Alright guys, so let's finish up our talk from yesterday about angular momentum. So we were saying that linear momentum, we remember, was given the symbol p, it was a vector, and it was mass times velocity. And angular momentum has a very similar form. It's the moment of inertia times the angular velocity. It's also a vector, and it has direction uh, in the angular momentum's direction is the same as the direction of the angular velocity, which is given by the right-hand rule. Um, so what I'd like to talk about today is conservation of angular momentum, um, and just a couple of quick notes. For the angular momentum to work out properly in the expressions that we're going to be using, we need to have the angular velocity be in radians per second. And also, for very similar to the principle of conservation of momentum, for angular momentum to be conserved, um, the net external torque acting on the system has to be zero. So it's okay if there's torques acting on the system that are external, but the net torque, the sum of all of them, needs to be zero. Um, and we won't consider internal torques because internal torques by Newton's third law are going to cause net zero changes in the angular momentum. So let's look at an example. So in this example, we've got two gears that are turning in different directions. They lie on a common axis, but they're not in contact with each other. And what we're going to do is we're going to force them into contact with each other without applying any external torque to them. So we're just going to sort of quickly slide them so that they're touching, but while we're doing that, we're going to make sure not to actually apply any torque that could resist a change in their rotational angular velocity. So we can use angular momentum conservation in this case because the way we defined it is that there isn't going to be any net external torque acting on the gears during what we could essentially think of as a collision. So we can say that the initial momentum is equal to the final momentum. The initial momentum is going to be given by the um, moment of inertia of each of the gears and their angular uh, velocity. So we're going to have the moment of inertia of gear A times its angular velocity plus the moment of inertia of gear B plus its angular velocity. And remember that these values are vectors, so sign does matter, and you might want to take a quick moment to look at the rotational direction of each of the gears and use the right-hand rule to show that the direction of the angular velocity is actually in the positive x-axis for both of the gears. When we're done, the gears will be moving together. So they're going to be pressed together, and friction between the two gears is going to cause them to eventually want to rotate at the same angular velocity. If they're rotating at different angular velocities, they're going to be sliding past each other, and an equal and opposite force acting on each of them from friction is going to bring them down to a point where they rotate at the same rate as each other. At which point there'll be static friction, or no friction necessary, sorry, so because they'll be rotating at the same angular velocity. So at that point, their angular momentum is given by their total moment of inertia times whatever their common angular velocity is. We'll call that angular velocity final. And if we wanted to find the final angular velocity, we could solve for it. And you'll notice that this equation looks very similar to an inelastic collision in a completely inelastic collision in a linear system where the two objects got stuck together. We had an equation that had a very similar form. So there we go. So that equation would give us the final angular velocity of the gears once they get stuck together. Let's try another problem that involves a collision that's not quite as straightforward. So here we have a bullet that's being shot, and it's going to eventually embed itself into a door. So this is a top view of a door frame, of a door, and then this is the hinge that the door is free to pivot about. And once the bullet embeds itself in the door is going to fly open and start to rotate with some angular velocity. And we're given some information about the system. The door has a mass of 15 kilograms. The bullet has a mass of 10 grams. The bullet is going to strike the door half a meter away from the hinge. The door's overall length is 1 meter. And let's try to solve for the velocity that the door will fly open at once the bullet embeds itself in the door. So initially this bullet is traveling in a straight line, so it has momentum, and we know the momentum of the bullet is given by mass times its velocity. An interesting thing though is that at the moment just before the bullet embeds itself in the door, we could think of the bullet as just beginning its new path of circular motion about the hinge. And so we could think of the momentum of the bullet just before it collides with the door as being angular momentum, because from that point on, the bullet will be traveling in a circular path. So the question is, well, how do we express the momentum of the bullet in terms of angular momentum? Well, let's say this is the hinge. Do an X so it's not confusing. And the bullet's sitting out here. If we imagine the bullet as a point mass, then we know the moment of inertia of the bullet is the moment of inertia of a point mass. And so that's going to be the mass times its distance away from the rotational axis, which they've given us the variable L. So mass times L squared. And that's our moment of inertia. So the angular momentum is equal to the moment of inertia times the angular velocity. And the angular velocity of the bullet is equal to its linear velocity divided by the radius. And so if we put this together, we'll get ml squared and then v over L. And simplifying that, we get an expression that we'll use pretty frequently, which is the moment of inertia, the angular momentum of a point mass, which could be expressed as mvl. And so that is the angular momentum of the bullet just before it embeds itself in the door. From this point on, we can think of this as an inelastic, completely inelastic collision, just like the example from before. So we're going to have some amount of initial angular momentum, some amount of final angular momentum. Initially, only the bullet's moving, so our angular momentum is the mass of the bullet times the velocity times L. When we're done, we're going to have the moment of inertia of both the bullet and the door times the common uh, angular velocity. If you look in your book, you'll find that the moment of inertia of a plank, a very thin plane about some rotational axis, if this distance is d, uh, your book lists the moment of inertia of that shape as 1/3 mass times d squared. So this is the moment of inertia of the door. If we put this all together, we can solve for the final angular velocity. It's going to be equal to mass velocity L over moment of inertia of the bullet plus the moment of inertia of the door. And let's see, what are we going to get? That's going to be 2.0 kilograms meters squared per second. And on the bottom, we're going to get 5 kilograms meters squared plus 0.0025 kilograms. Remember that the bullet was measured in grams, not kilograms. And all of that together is going to give us a final angular velocity of the door of 0.40 radians per second. So the general concept of the problem is very similar to the first example. We're basically doing a completely inelastic collision for angular momentum, but we had sort of a new thing here, which is trying to understand the linear momentum of the bullet in terms of an angular quantity just before it embeds itself in the door. We could also go a step further and find the amount of energy lost during the collision, which is a really common question for these types of problems. So the initial kinetic energy was all from the bullet, and that would be 1/2 mass times velocity squared. And if we plug in the values, which is the 0.01 kilogram bullet and the 400 meters per second as the velocity of the bullet, we'll get 800 joules. The kinetic energy after the collision would be 1/2 the total moment of inertia. So the moment of inertia of the bullet plus the moment of inertia of the door times their common angular velocity squared. And when we plug in all of those values, we're going to get 0.40 joules. So if we do the ratio of the final over the initial, we get that the final kinetic energy is about 1/2000th of the initial. So we lost quite a bit of energy during the collision.